For centuries, humans have speculated about the possibility of life beyond our own world. Thanks to the James Webb Space Telescope, JWST, the most advanced telescope ever built, that age-old question may finally be within reach of a real answer. While observing Proxima Centauri, the nearest star system to Earth just 4 light-years away, scientists have detected something extraordinary from one of its planets. Proxima B, unusual anomalies believed to be artificial lights, have sparked both scientific intrigue and widespread curiosity. But what exactly are these lights? Could they indicate the presence of intelligent life? Join us as we delve into the James Webb Space Telescope's unsettling discovery of what might be city lights on a distant world, an observation that could redefine our understanding of the cosmos. Currently, Earth remains the only known planet to host life. Since the dawn of civilization, humans have wondered if life exists elsewhere in the universe. In pursuit of that answer, American astronomers Jill Tarter and Thomas Pearson launched a search for extraterrestrial intelligence SETI in 1984. The mission aims to detect radio signals from outer space, waves capable of traveling vast distances, and picked up by the 42 telescopes comprising the Allen Telescope Array in California's Sierra Nevada mountains. So far, no conclusive alien signals have been detected. The launch of the James Webb Space Telescope, however, has reinvigorated the search. Orbiting about 1 million miles from Earth, JWST is equipped with highly sensitive instruments capable of scanning a wide variety of exoplanets orbiting distant stars. Its unprecedented power positions it to make breakthrough discoveries. Just a few decades ago, no planets outside our solar system had been confirmed. Today, over 4,000 exoplanets have been identified, and NASA estimates that the universe could contain millions more. One early method for identifying signs of life is to look for extraterrestrial vegetation. For example, when NASA's Galileo spacecraft passed by Earth on its way to Jupiter, it turned its sensors toward our planet and detected a unique biosignature known as the vegetation red edge, a combination of red and infrared light reflected by plant life. A jungle-covered planet would produce a strong and distinct red edge signal. JWST is expected to measure the same red edge signature on Earth-like exoplanets located in habitable zones, the regions around stars where liquid water can exist. As starlight passes through a planet's atmosphere, JWST can use spectroscopy to analyze what elements are present based on how the atmosphere absorbs certain frequencies of light. Each molecule absorbs a unique range of frequencies, creating a distinct spectral fingerprint that reveals the composition of the atmosphere and potentially whether it supports life. If a planet has an Earth-like atmosphere made up of oxygen, nitrogen, and carbon dioxide, it may be a promising candidate. Even more compelling would be the detection of artificial compounds not naturally found in nature, such as chlorofluorocarbon CFCs, chemicals used in refrigeration and cleaning. If extraterrestrials observed Earth, CFCs in our atmosphere would likely signal technological advancement. If JWST detects similar compounds elsewhere, it could be a powerful indication of intelligent life. However, extraterrestrial life may look nothing like what we're familiar with. Some forms of life, known as extremophiles, can survive in environments that would be lethal to most organisms. These resilient microbes thrive in extreme conditions, such as temperatures above 250 degrees Fahrenheit, or in acidic environments with pH levels below 3. Still, planets that resemble Earth, those with moderate temperatures, liquid water, and stable stars, are considered our best chance for discovering life. Our Sun is a G-type yellow dwarf star, a stable category that offers the right conditions for life to evolve. Other similar systems are prime targets for future exploration. Red dwarf stars generally have shorter lifespans, but in our universe, they are far more common than stars like the Sun. Their lower luminosities and cooler temperatures make them prime targets for studying orbiting exoplanets. Because red dwarfs burn their fuel slowly, they can exist for billions of years, providing a long time window for life to develop and evolve into complex forms. One of the most exciting subjects of the James Webb Space Telescope, JWST, is the TRAPPIST-1 system, located about 40 light-years from Earth. This calm red dwarf star hosts 7 Earth-sized rocky planets. 3 of them lie in the so-called habitable zone, where temperatures might allow for the existence of liquid water on the surface. Although the TRAPPIST One star is smaller and cooler than the Sun. Its proximity to its planets allows it to emit enough light, comparable to what we receive on Earth during Sunday afternoon sunlight. Another key target in the search for extraterrestrial life is Proxima Centauri, a red dwarf star just 4.25 light-years away. Due to its dimness, any planet would need to orbit much closer than Earth does to the Sun in order to maintain liquid water. In August 2016, astronomers discovered such a planet, Proxima B, with a mass about 1.3 times that of Earth, located in Proxima's habitable Goldilocks zone where conditions may be just right for liquid water. However, Proxima B orbits extremely close to its star, only about 4.66 million miles away, which makes it vulnerable to intense stellar winds that could strip away its atmosphere. Even so, it still receives enough solar energy for liquid water to potentially exist, assuming it has an atmosphere to trap heat. Due to its proximity, Proxima B is believed to be tidally locked, meaning the same side always faces its star, much like how the moon always shows the same face to Earth. Proxima Centauri is only 18% the mass of our Sun and emits just 5% of its brightness. From a distance, Proxima B may seem like a scorched, barren planet. Yet, if it retains protective atmosphere, surface water could still exist. The planet gets about 65% of the solar energy Earth receives, enough to support life in theory, though the environment may not be particularly hospitable. Tidal locking causes permanent day and night sides, leading to extreme temperature contrasts. Moreover, Proxima B receives nearly 3 times as much high-energy radiation, including X-rays and ultraviolet light, as Earth. It is constantly bombarded by solar flare particles, which would be dangerous unless the planet possesses a strong magnetic field similar to Earth's. Whether Proxima B has favorable conditions for life remains uncertain. Atmospheric models suggest that tidally locked planets may lose their atmospheres quickly due to the freezing of volatile gases on the cold, dark night side. On Earth, volcanic activity helps replenish the atmosphere, and a robust magnetic field prevents its escape. Since we don't yet know whether Proxima B has either active volcanism or a magnetic shield, we cannot say for sure whether it still has an atmosphere. An atmosphere would suggest the possibility of oceans, and both would indicate that life could potentially exist. Optimists imagine that, if inhabited, the planet's sunlit side might host solar-powered charging stations to generate energy, which could be used to heat and illuminate the cold night side. The discovery of Proxima B has generated considerable interest in determining whether it ever transits across the face of its star as seen from Earth. If so, scientists could study the dimming effect during the transit to estimate the planet's size and mass, revealing its density and confirming whether it's truly a rocky planet. They could also analyze any starlight passing through its atmosphere for signs of chemical compounds. However, the odds of a perfectly aligned transit are low, only about 1.5%. Further complicating this effort is the star's volatility. Frequent solar flares make consistent observation difficult. As astronomer David Kipping from Columbia University notes, Proxima Centauri is highly unstable. Its flares cause rocky planets to absorb sunlight and re-emit it, complicating the detection of subtle signals. Infrared light and the search for life on Proxima B. Rocky planets like Proxima B emit a distinct type of infrared radiation, particularly when orbiting stars such as Proxima Centauri. The James Webb Space Telescope, JWST, specifically engineered to detect infrared light, is perfectly suited for observing such signals. Proxima B's infrared signature is crucial for identifying the presence and composition of its atmosphere. In fact, JWST's infrared capabilities far surpass those of its predecessor, the Hubble Space Telescope. This means it could potentially detect artificial city lights on Proxima B's night side, even if they're as faint as Earth's. If these artificial lights fall within a narrow frequency band distinct from the star's natural light, JWST may be able to pick them up. Some scientists even hypothesize that Proxima B's day side might be covered in solar panels designed to harvest energy from its star. Because the planet is tidally locked, constantly showing the same face to its star, it experiences extreme temperature contrast between its permanent day and night sides. The degree of this temperature difference reveals critical clues. If the planet lacks an atmosphere, the day side would emit all the absorbed energy as blackbody radiation, while the night side will resemble a frozen desert. However, if there's a smaller contrast between the two, it may indicate the presence of an atmosphere that distributes heat. Amazingly, JWST could collect enough data in just 11.2 Earth days to detect potential artificial lights on Proxima B's night side. Lights that might hint at intelligent life. If confirmed, such a discovery could suggest the existence of a technologically advanced civilization that harnesses solar energy during the day and illuminates its environment at night. Still, scientists are cautious. While the presence of artificial lighting would be extraordinary, there are many natural phenomena that could produce similar signals: reflection from surface features, volcanic activity, lightning storms, or atmospheric anomalies. Since JWST's exoplanet detection technologies are still in their early stages, continued observation and verification are essential. Researchers plan to monitor Proxima B and other potentially habitable exoplanets to build a broader understanding of their environments. Even if artificial lights are detected, confirming their origin will take years of further investigation. Should the signals be traced back to intelligent life, it would mark one of the most profound scientific breakthroughs in human history. The fascination with Proxima B and exoplanets in general goes beyond the hope of discovering alien life. It raises deep philosophical questions about our place in the cosmos. The confirmation of extraterrestrial intelligence could reshape our understanding of life's uniqueness and spark global cooperation rooted in shared curiosity and wonder. Such a discovery would not only validate our drive to explore space, but also accelerate investment in advanced technologies and interstellar missions. For now, the search for city lights on Proxima B is a thrilling possibility, one that brings us closer to answering one of humanity's oldest and most profound questions. Are we alone? As JWST continues to return data from distant worlds, the vision of finding intelligent life grows ever more tangible. Whether Proxima B is home to an advanced civilization or not, the insights we gain will guide the future of space exploration and may one day lead us to a universe more alive than we ever dared to imagine.